Welcome to chapter 4.2, where we're going to continue looking at graphs of the sine and cosine functions, and I'm going to give you a more simplified method that builds on what we did in 4.1. We'll kind of use this table method for the other functions as well, and hopefully by using one simplified method, very systematic method, this will make the graphing much more simple for all the trig functions. So we're going to look at the table method for graphing, and then we're going to add some translations. And this is when the graph slides horizontally to the left or right, when the graph slides vertically going up or down, and then when we combine these translations where it goes up and left or down and right, etc. So the basic table is this. This is for the sine and cosine graphs, meaning that the top row, the rows that you see in yellow, will be specific to these functions. The top row are the key values for sine and cosine. Notice these are our quadrantals. 0, pi over 2, which is 90, pi, which is 180, 3 pi over 2, which is 270 degrees, and 2 pi, which is 360 degrees. These are the quadrantals are the key values on our quadrantals on the unit circle. And then the function values you see here, the sine and cosine values for each of those corresponding angles. Okay? The model, the equation model, is y equals c plus a sine times the quantity of b times the quantity of x minus d. Okay? And this works for sine and cosine interchangeably. Where the first constant here, the first variable c, is the vertical shift, the shift up or down. The second variable you see is the variable a, which represents the amplitude shift, which we saw in 4.1. D is the horizontal shift, left or right. This is also known as a phase shift when we're talking about these circular functions in trig. And b is the period constant, which we also looked at in the prior section. Note that by making d negative in the equation, this adjusts for the opposite effect, if you will. So if d is negative, then the graph will shift in the positive direction, and if d is positive, it will shift in the negative direction. This is explained a little bit more by this comment at the bottom. So if when you write the function you have a plus d here, instead of the minus d that's in the model, then we're going to need to subtract d in this third row here. Notice it says the horizontal shift. We're going to use the above values plus the d variable. Okay, and you can see that what's happening here really is d is going in the opposite direction. So if you have minus d, it's actually going in positive direction. If you have plus d, it's going in the minus direction, in the negative direction, excuse me. And you can see this by if you rewrite this. If you rewrite x plus d to make it x minus d, then we have to do x minus minus d. And so you can see then we would subtract d in that case. Okay? This is a good overview slide. It probably doesn't make a lot of sense right now, but hopefully as we go through this with multiple examples, it will. Horizontal translations, as we remember from algebra, are when the graph shifts, to the left or to the right when we add or subtract a constant inside the function as the argument of the function. So we can see the graph of the function f of x minus d is translated horizontally compared to the graph of y equals f of x. We can see that when we add 3 inside the function f of x, we actually move in the negative direction 3 units. When we subtract 4, we shift the original graph of f of x to the right or the positive direction 4 units. So we can say that the translation is d units to the left if d is greater than 0, f of x plus d, or it's d units to the right in the positive direction if d is less than 0, or you have a function f of x minus d. Okay? Be really careful here. This is counterintuitive. Plus goes in the negative direction, etc. I'm going to try to help you keep focused on this. And maybe the best thing is to rewrite all equations so that they are in this model of f of x minus d. So if you have a negative, this would be x minus, I'm sorry, if you have a positive, x plus d, if you have f of x plus d and you want to write this as minus, this would be f of x minus a negative 3. And then you can kind of see that the direction is more intuitive if you always write it as a difference problem. All right, we're going to look at that. With circular functions, these horizontal translations are called phase shifts, as I mentioned before. And in the function y equals f of x minus d, the expression x minus d is the argument. So we're really talking about the argument of the trig function. So for example, sine of x minus d, cosine of x minus d, tangent, etc. Okay, so let's look at this for a simple problem. Okay, so here we have y equals the sine of x minus pi over 3. Okay, and we want to graph this over one period. Okay, we're going to use the table method, and although this model is more comprehensive, I'm going to use it throughout, so I'm not changing the model for each time. Here they just simplify the model, but I want you to get into the habit of identifying all 4 variables. The vertical shift, the amplitude, the period adjustment, and the horizontal or phase shift. Okay, so that's really the first thing we're going to do, is try to figure out what are each of those variable values. So notice the value, the multiplier in front of sine is 1, so a equals 1. The multiplier outside this parenthesis of x minus pi over 3 is also a 1, so our period shift is equal to a 1. Our constant in front, there is no constant in front, so this is like 0 plus, so c equals 0. And then we can see here that d equals pi over 3. Okay? So the first step is to look at the model and to identify those key values. Now, a, b, and c really have no effect. When you multiply by 1, you don't change the value, so the amplitude is not being changed. When you multiply or divide by 1, again, you don't change the value, so the period is not being changed. And we're not adding a constant for the vertical shift, so we're going to move up or down 0 spaces, which of course means we're not moving at all. So really, with these 3 values of a equals 1, b equals 1, and c equals 0, we really haven't shifted the period, the amplitude, or the vertical graph here. Okay, so then we're going to build our table. Okay, I'm going to walk through this. I don't have a way of building this out. Okay, so our table has this first value input. These are our quadrantals, and it has, in this case, we're dealing with sine, so we've put the sine values in there. We're going to walk through the table. Since the b variable is equal to 1 and dividing by 1 will just give us these same variables, I've just left it blank. So we're going to use the top variables. The next thing that we do in this table is identify any phase shift. And this is the period, the row above, in this case 2 rows above because we didn't have any period adjustment. We're going to add d to this. Now remember, d is pi over 3. Excuse me, so we're just going to add pi over 3. 0 plus pi over 3, pi over 3. Pi over 2 plus pi over 3, we have to have a common denominator of 6, and when we do that, we get 5 pi over 6. Pi plus an additional 1/3 pi, or pi over 3, gives us 4 pi over 3. 3 pi over 2 plus pi over 3, again, we need to have a common denominator of 6, and we get 11 pi over 6. And then finally, if we have 2 pi plus pi over 3, we're going to get 7 pi over 3. Now, I'm not going to walk through these, how to add these fractions, etc. You need to be able to do that. Okay? The sine values are given. These are the same sine values for the quadrantals. At 0, it's 0. At pi over 2, it's 1. So this is just built into the table. Okay? We don't, again, we're multiplying the sine values by 1 for the amplitude, so they don't change, so I didn't put that in there. And c equals 0, we're adding that to above, it doesn't change. So there's no reason for me to fill in these lines and just duplicate that. We really only had a phase shift here, okay? So the top 3 rows are your x values, the bottom 3 rows are your y values, and so we didn't have any change in the y values because we didn't have an amplitude variable that changed anything or a vertical shift that changed. So these are the values that we're going to graph. We're going to graph pi over 3 at 0, 5 pi over 6 and 1, 4 pi over 3 and 0, etc. And that's what you see here, okay? And that's graphing a phase shift, pretty much a phase shift only. That's probably one of the simpler problems, okay? The method 2 here is simply recognizing that we don't have an amplitude adjustment, we don't have a period adjustment, we don't have a vertical constant added outside of this or subtracted, so we only have a phase shift. So what method 2 is here is recognizing that if we look at the graph of sine x, which is in red here, we can see that we're simply moving in the positive direction. Remember, this is counterintuitive. We're moving in the positive direction by pi over 3. So if we just shift this entire sine curve to the right, 1/3 pi, or pi over 3, we get the new graph. That's fine if you only have a simple change like a phase shift or a vertical shift. Okay. So let's look at another example. It's getting a little more complicated. So we're going to do the same thing again. We're going to make sure that we have the right model. So the first thing we want to do is to make sure to identify all of the key elements. Okay. So again, our amplitude. Now we have a multiplier in front here. Okay, 3. Notice this says sine, but remember we can put sine or cosine in the model, so it doesn't matter. The amplitude is 3. The multiplier in front of x plus pi over 4 is 1, so b equals 1. There is no constant being added outside of the cosine function or subtracted, so c equals 0, the vertical shift. And then d, now be careful here, remember d is the opposite, it's not in this format. If we rewrote this, it would be x minus negative pi over 4. So d equals negative pi over 4. All right, this is the counterintuitive part. So if we're adding, it's actually a negative in there. Okay, we now build our table and we'll walk through this. Okay, notice again the top value is given in the sine and cosine table, actually in all the tables. And then, of course, the cosine values, because that's the function here. The key values for sine and cosine are the quadrantals, 0, 90, 180, 270, 360, or in radians, as you see. And then, of course, the cosine values correspond to them. Cosine at 0 is 1, at 90 is 0, etc. Okay? So the top row and the 4th row are given. Now we work our way through the table. Since b is 1, and we divide by 1, this isn't going to change the value of the angles, the top row. So I'm just putting dashes in there. But we do have a phase shift again. It's negative pi over 4. So we're going to subtract, plus a negative pi over 4 is minus pi over 4. Okay? I've got this star here to remind you that this is counterintuitive, so pay attention to it. Since it's x plus pi over 4, we actually subtract pi over 4. 0 minus pi over 4, negative pi over 4. Pi halves, pi over 2 divided by pi over 2 plus negative pi over 4, or subtract pi over 4 gives me 1/4 pi, or pi over 4. A whole pi minus 1/4 pi gives me 3/4 pi. 3 pi over 2 minus pi over 4 is 5 pi over 4. And 2 pi, which is 8 pi over 4, minus a pi over 4 gives me 7 pi over 4. Again, I'm not going to work through these fractions. You should be able to subtract pi over 4 from each of these quadrantal angles. Okay? Again, our cosine values are plugged in there. The next thing we do is we multiply a times those values above. Well, A in this problem, the amplitude is 3, so we just multiply 1 by 3, 0 by 3, negative 1 by 3, 0 by 3, 0 times 3 is 0, and 1 times 3 is 3. Again, we do not have a vertical shift. There's no plus 3 out here or negative 3 plus a sign, etc. So I left that blank. So now our x values are the ones that we got at the bottom of the 3 rows, the phase shift, and our y values will be the amplitude values because we didn't have any vertical shift. We plot these. For example, the first point would be negative pi over 4, 3. And here you can see that, negative pi over 4, 3. All right. And then, of course, we're just going to connect the dots with a smooth curve. All right. Let's try one that's a little bit more involved. Okay. 3 times the cosine of x plus pi over 4. Well, here you can see they've rewritten this problem so that it actually fits the model, so that always the argument is in minus form. So we get x minus a negative pi over 4, and then we can see why we shift actually to the negative direction, because the phase shift, d, is actually equal to a negative pi over 4. Okay? So if we graphed 3 cosine, just the cosine, which is here in red, this is just 3 cosine x. So this is just cosine with an amplitude of 3. Then we know that because we only have an amplitude and a phase shift, then all we have to do is graph 3 times cosine and then shift it to the left by pi over 4. All right. To me, again, it's much easier to do the table because that works every time. It's very methodical, and in my mind, it actually requires a little bit less thinking. Okay. And also notice when the trig functions become more complicated, and what I mean by that is that you have values for multiple variables. Here we had a value for amplitude, and we had a variable for the phase shift, for A and for D. I would say as soon as you have 2 of those, stop and just use the table. You can use the table every time. It'll always work. And it's much more methodical and step by step. All right, let's look at another one. Graph y equals negative 2 cosine times of the quantity 3x plus pi. All right. Now, I want you to notice this because this is really key. Whenever you have a equation like this, a trigonometry equation like this, and we're trying to graph it, we have to make it match the model. Notice that we should always have x by itself without any multiplier, okay? That multiplier has to be outside the parentheses. Otherwise, our phase shift variable is going to be inaccurate. This looks like a phase shift of pi, but it's not really if we rewrite this. So we want x to be alone inside the parentheses with the phase shift. So we have to factor out a 3 here by rewriting it. And this should always be your first step, is to check that the equation given you looks like the model. Okay? So again, here we want to rewrite this. We want to factor out the x. The 3. We factor out 3, we get 3 times the quantity of x plus, if we take 3 out of pi, we get, which means dividing by 3, we get pi over 3. I could take this one more step further and make sure that my phase shift variable also uses a difference. And so x plus pi over 3 is the same as x minus negative pi over 3. Once I've done this and rewritten the equation to match the model, now I can identify my key elements. And I can see that my amplitude, or A, is negative 2. My phase adjustment, B, is 3, is equal to 3. I don't have any constant being added or subtracted outside of the trig function. And I can see that my phase shift is negative pi over 3. Having identified all of those variables, I'm now ready to build my table. And you can see each time, with each example, it's getting a little bit more complicated, and we're using all the rows. And as you can see, you can use the table without any of these values or with all of them. Okay, so the first thing we know, the first row is given, quadrantals. The fourth row is given cosine values for each of those quadrantals. All right. The first thing we have to do is a period adjustment. We take the key value, kV, divided by the variable b, in this case, which is 3. 0 divided by 3, 0. Pi over 2 divided by 3. Dividing by 3 is the same as multiplying by 1/3, so we get pi over 6. Pi divided by 3, 3 pi over 2 times 1/3. The 3's cancel out. I get pi over 2. And 2 pi divided by 3 is actually 2 pi over 3. Okay? Now we take the period values and add our phase shift variable because we're shifting to the left or the right. So 0 plus negative pi over 3, negative pi over 3. Pi over 6 minus pi over 3, minus pi over 6. Pi over 3 plus negative pi over 3, 0. Pi over 2 plus a negative pi over 3 is pi over 6. And 2 pi over 3 minus pi over 3 gives me 1 pi over 3 left. Okay? These are going to be our x values since we used all 3 rows. The bottom row that we use will be the one that we use as our x values. The next 3 values, the rows, are our y values. And again, we'll go to the bottom row that we use. The cosine values were given. And then the next row tells us to multiply those values times the amplitude, which in this case was a -2. A equals -2. All right, so we get 1 times -2, 0 times -2. -1 times -2 is +2. 0 times -2 is 0. And 1 times -2 is -2. Okay, again, c equals 0, so adding 0 to these values doesn't change anything. And now we have our values that we're ready to graph. Our x values, the bottom row from the top 3. Our y values, the bottom row filled in from the bottom 3. And we get these points here. Okay? Now, this asked us to graph it over 2 periods. And so notice what they did here. They just extended the graph to the left and to the right to actually give us 2 periods, 2 of the same graph. That was actually kind of clever and interesting. So they didn't even really plot any more points. They just extended the graph to the right, back up to the maximum, and to the left, back up to the maximum, recognizing where it would cross the x-axis. Okay. Our last part of this graphing of sine and cosine is the vertical translations, okay? And this is when you're adding a constant outside of the function. Remember before, for the horizontal or phase shift, it was f of x plus a constant, f of x plus d or f of x minus d. Here we have the constant outside, so this is just taking our graph up the y-axis or down the y-axis. 3 plus f of x is f of x shifted up 3 units. -5 plus f of x is shifting the graph down 5 units. Okay? What's nice about this is very intuitive. If you add something, it goes up. If you subtract something, it goes down. All right? So let's see how this works with an example. We have y equals 3 minus 2 cosine 3x over 2 periods. Again, the first thing we want to do is make this look like the model, okay? This isn't really that different, but I just went ahead and pulled out the b instead of just having it be 3x. 3 times the quantity of x minus d. Since it's just x, then d would be 0, etc. But now it looks like the model that we have for our table, a, b, c, and d variables. And so here we can see our amplitude is -2. Our period adjustment is 3, the multiplier in front of the angle. Our vertical shift We have a 3 outside that's being added to this, 3 minus 2. This may sometimes confuses students, but notice if we had negative 2 cosine 3x, we could put the 3 afterwards, so it would be negative 2 cosine 3x plus 3. The 3 is positive. It's subtracting the rest after, which means that our amplitude is a negative 2. And then, of course, because there is no shift inside here, it's minus 0, then d equals 0. Once we have those 4 key elements / variables identified, we're ready to build our table. Again, the first row is already given because it's the quadrantals. The fourth row is already given. These are the cosine values. Yes, we're doing cosine again for those 4 values. Make sure you're using the right values, cosine or sine, in your table. Okay? First thing we're going to do is adjust the period. The period adjustment is by a 3. Okay? So we're going to divide each of these key values or angles by 3. 0 over 3, still 0. Pi over 2 times 1/3. Dividing by 3 is the same as multiplying by 1/3. Pi over 6, etc. And we get those angles. There is no phase shift, so I've left that blank. So the row number 2 will be our x values. Remember, the first 3 rows, we're calculating the x values. The second 3 rows, the last 3 rows, I should say, we're calculating the y values. Okay? The cosine values are given for the quadrantals. Then we multiply by the amplitude factor, which is negative 2. Negative 2 times 1, negative 2 times 0, negative 2 times negative 1 is positive, etc. The last thing we do is to add any vertical shift, and this is that constant of 3. So we're going to add 3. Negative 2 plus 3 is 1. 0 plus 3 is 3. 2 plus 3 is 5. 0 plus 3 is 3. And negative 2 plus 3 is positive 1. Again, we can see our x values are the second row. And since we used all rows at the bottom, the very bottom row is our y values. And this is what we will be graphing. 0, 1, pi over 6, comma 3, etc. All right. So that's what you see to the right here. This did ask us to graph it along for 2 periods. So what they did is they just matched the graph on the right side of the y-axis and mirrored it on the left side. Much easier than trying to figure out more points, although you could figure out the same points here. Okay? We're always looking at 0, 1s for sine and cosine anyway to match them. So just a quick reminder of how we're doing this. First, rewrite the expression to match the model. And again, it doesn't matter if it's sine or cosine, these are interchangeable. Just make sure you're using the right one and the right table with the right values. Then you want to identify the key variable or graph parts from the model. A, B, C, and D. A is the amplitude, B is the period adjustment, and make sure it's outside of the parentheses when you're multiplying times x, okay, because that will affect the period shift. I'm sorry, it will affect the phase shift. C is your vertical shift, any constant outside of the function, and D is your phase shift, which is also the shift left and right or horizontally. Once you've identified those, you're going to build your table with the given first and fourth row, and then fill it in 1 row at a time depending upon the values of the graph variables. And then extend the graph over additional periods as needed. And we saw a couple different methods for doing that. So again, I just kind of want to remind you how this looks. This is that first slide we looked at for the table method. Again, the first row and the fourth row are given. And then we're going to find the x values to graph with the period shift, the key value divided by b. Find the x values. We're going to shift those again by looking at any horizontal shift by adding d, our phase shift variable, to the above x values. And then we start over with the y. We have a given y values for the quadrantals. We multiply that by the amplitude and then add our vertical shift constant to that. Okay. And again, be careful with the d variable. This is the one that's probably the most difficult to do, and also sometimes b, to make sure that you've pulled it out in front of the parenthesis for the argument. All right, so let's look at something that combines everything. All right. So we have y equals -1 plus 2 sine of the quantity 4x plus pi. All right. Again, we don't have x alone here, so we know we have to rewrite this. We also don't have a minus d, we have a plus, so we might want to rewrite that as well. Okay. Here we've rewritten everything except for the phase shift. It's still positive. So it's okay by me to do that because I always remember that the phase shift is counterintuitive. It's the opposite direction. But if you want to be OCD or perfectionist, this would be x minus -pi/4. So d is equal to -pi/4. We need to identify the variables. Our amplitude is 2. Our period factor is 4. Our vertical shift c is -1. And again, our phase shift is -pi/4 because it's the opposite here. If we rewrote it here, we'd see it's minus a minus, so we get that. All right, once we've done that, we build our table. And here we finally have a complete table. All right, it's not that difficult as long as we have this in the right form. Okay. The first row is given. The next thing we're going to do is divide by b. Dividing by 4 is the same thing as multiplying by 1/4. 0 times 1/4, pi/2 times 1/4, pi/8. Pi times 1/4, pi/4. 3 pi/2 times pi/4. I'm sorry, times 1/4. Let me slow down there. Gives me 3 pi/8, and 2 pi divided by 4 gives me pi/2. We then add in our phase shift, which is d, and d is -pi/4. 0 minus pi/4, minus pi/4. Pi/8 plus a -pi/4 is -pi/4. Pi/4 minus pi/4 is 0. 3 pi/8 minus pi/4, we need to change this into eighths, which gives us -2 pi/8. 3 pi/8 minus 2 pi/8 just leaves pi/8. And pi/2 minus pi/4 gives me pi/4. So I did some of those, I didn't do them all. The fourth row is given. We are now doing sine. So we have our sine values. You need to make sure you're using the right table. The only thing that's going to be different are these values in yellow here, okay? Because cosine values will start with 1 and alternate. We multiply that then by the amplitude, which was 2. So 0 times 2, 1 times 2, 0 times 2, -1 times 2, and 0 times 2. We then add our vertical shift constant, which is -1, c. 0 plus -1, -1, 2 plus -1, 2 minus 1 is 1, 0 plus a -1, -1, -2 plus a -1 is a -3. Be careful there. And 0 plus -1 is -1. We now have our x values, the third row, the bottom row of the top 3, and our y values, the bottom row of the whole table, since it's all filled in. This is what we'll graph. And here we can extend the graph to the right and to the left. They did the same thing here, just a little bit, shifting it so that you would have 2 full periods. All right, this is the last slide. It's a little bit long lecture, I know, but we did the same thing over and over again, and I thought that was really important for this table version of solving these graphs.